It's going to stop at probably 22 minutes. Any questions?
Well, no. What are we doing Wednesday? Do you know?
No, I don't.
Okay.
Probably would have been a good time to do that multiple choice test. Other questions? All right. We last left off with this idea that electrons have wave properties. So is it a wave? Is it a particle? Well, it depends. I know that for light, we have these relationships here for electromagnetic waves. Then we've exploited the HF quite a bit. Again, H is Planck's constant, which is 6.626 times 10 to the negative 34th joule seconds. Although the units I gave you before were in the base units, or what formally referred to as base units. I know that frequency times the wavelength is equal to the speed, well, the speed of light. What form do I want this in? Okay. And so from this, I know that the frequency is equal to what form do I want it in? I feel like I have something upside down here. No, that's right, that's right. Good there. That's redundancy written down here. Oh. Sorry. The wavelength, that's what I'm shooting for, is equal to C divided by the frequency. From this up here, I know that the frequency is E over H, or PC over H. I make that substitution. Probably the second one is the one I want. So I have C over PC over H, which is just H over P. It's just manipulation of letters, but think about the implication of it. As you were walking down the street, what is your wavelength? Now you could make the argument, depends on if anyone is observing you. And then the philosophical question of, can you collapse your own wave function? Can you decide if you're a particle or a wave? In the movie, it was a spoof of superhero movies with Ben Stiller. Blanking on the name of it. Anyway, there was a character in there who if no one was observing him, could not be seen. He was invisible if no one was observing, in essence. I think it's a quantum thing. But you're walking down the street, so let's say average adult, 70 kilograms. Walking down the street, 1 meter per second is a nice number to work with, even though that's probably, if it's a simple stroll, probably a bit much. So the magnitude of your momentum is 70 kilogram meters per second. So the wavelength would therefore be 6.626 times 10 to the negative 34 joule seconds divided by 70 kilogram meters per second. And we get, if someone would be kind enough,
.46 times 10 to the negative 36.
units.
Meters?
Yeah. Okay, so this is, if you think about it, the size of a nucleus is about on the order of 10 to the negative 15th meters. And so we are talking about significantly less than this size of the nucleus of an atom. So there is a somewhat unrealistic aspect to it. We cannot test this. However, when you're dealing with smaller particles, like an electron, which has a mass on the order of 10 to the negative 31st and a velocity or a speed that's not going to be bigger than 3 times 10 to the 8th, we start dealing with things that actually can be tested, and as mentioned last time, were tested.
When we're talking about like just walking, what is a waveform? Like what are we measuring with that?
It would be that if no one were observing you, and you came across a very thin barrier, you could walk on both sides of it and reform on the other side.
At the same time?
I hope so. If you didn't do it at the same time, then you'd be sort of out of sync, which would either kill you or just be creepy looking. The idea that a particle can take more than one path at once is a strange concept. But when you deal with, especially with elementary particles, it can take two paths at once.
Okay.
That was one of the bases for my dissertation. You seem unsettled.
I believe you. I just with the human analogy, it's just a weird picture.
When I was brainwashing my son, when he was young, I had this story of the quantum lion that would jump through, 2 windows at once and behave some wave and particle characteristics.
Is your son okay?
I don't know. He became a physics major, so there's a certain amount of insanity right there. He's now having kids in trouble. Perhaps it's so that they avoided the mistakes he made. When is it too young to teach kids about quantum physics?
The ripe age of 6 years old.
6 years old? Yeah, okay.
When they can talk and remember things.
All right. So we have now this idea that things can be waves and particles. So how do you actually describe it? So I'm going to draw a wave on the board here. I haven't done it yet. All right. Assuming that I drew it properly, if I asked you what's the wavelength, do you think you could find it? Why not?
Wave is bigger. It's not consistent.
I heard because the wave is bigger than the
Wavelength,
velocity.
it doesn't look consistent.
Well, that's why I threw it, assuming I drew it correctly. Assuming that it's consistent,
So,
would you be able to, if I handed you a meter stick, find the wavelength?
still probably not. I don't have faith in my
Okay, besides Micah, does anyone think that they could actually measure the wavelength if I handed them a meter stick? This is not meant to be a trick question. Still no.
I think you can, it's just the distance for the wave, like with the, you would measure one
That-
period, I think.
Well, period wavelength are different.
I said no because there's no origin for me to go off. Maybe.
You don't need an origin to find the wavelength.
No.
I can do it
How would you do it?
from peak to peak.
Yeah,
Oh,
Yeah.
okay.
not meant to be a trick question. Assuming that the wave were drawn regularly with the same wavelength, that this is a physical wave here, as opposed to this is not first time, but first position. And it went off in both directions forever. And despite the need for some of you, for me to actually draw it on farther, I won't draw on these walls yet. All right, where's the wave?
Everywhere and nowhere.
All right. We'll just stop at your first answer, everywhere. Or at least it extends on forever. In other words, if I can identify the wavelength, if this is drawn regularly and just it spreads out, I can identify the wavelength relatively easily, but finding the position of it is a lot harder to do. Meanwhile,
Or can we like say it is wherever we say it is?
no, I mean, the wave actually is, if I drew it forever, it would be everywhere.
Okay.
Or at least along that plane. All right, I got another wave here. Do you think you could at least narrow down the location of that wave?
Yes.
Okay. Finding the wavelength?
You could, but it's harder.
Yeah. So the more I have an idea of what the location is, the harder it is to find the wavelength. And vice versa. I can find the wavelength over there, but not the location particularly easily, but the location here, I got a pretty good idea of where it is. I can narrow it down. So this duality here, the fact that the more I know of one thing, the less I know of another, is a common principle and known as Heisenberg's uncertainty principle. Learning to spell certainty. Sure. This is actually a major principle, and this is one of the reasons why in Star Trek they have what is referred to as the Heisenberg compensator. Because when you are beaming someone from one location to another, you might know where the particles are, but you lose other information. If you know the location, you lose other information about it.
Did you mean Star Trek?
Pardon?
Did you mean Star Trek?
What did I say?
Star Wars?
Oh man, might have to edit that out. Yes, I definitely meant Star Trek.
I was like, that's definitely Star Trek.
That is. I apologize. Yeah, that's inexcusable. I thought Star Trek. Wow. I didn't record the last embarrassing Star Trek moment. Someone made a Star Trek reference. Missed it, then it was a Star Trek reference. Classic Star Trek, not that crap that J.J. Abrams does. Okay. So let's go do a pseudo derivation of Heisenberg's uncertainty principle. Speed, what's the formula for speed?
Distance over time.
Yeah. So delta x would be the location of this object. And that's just going to be equal to the speed times however much time passed by. Speed was the relationship between speed and momentum.
Oh, momentum over mass.
Okay. So this is just momentum over the mass times delta t. Solving for delta t, which I could have, I guess, skipped a step and done it there. That's just going to be mass over the momentum times delta x. Yep, I did that right. I know that the relationship between, which wasn't written up over there, the relationship between the wavelength and the momentum. There's a whole lack of confidence that I'm going to write everything correctly. And since we're dealing with x, let's just go ahead and put a little subscript x there. So we're going in circles here. Oh well. I know frequency times wavelength is equal to the speed. So frequency is equal to the speed over the wavelength. And I have two equations which I have now made completely separate from each other. I just will bring this with me so I keep walking back and forth. Speed, I know, is p divided by m. Wavelength, I know, is v divided by the wavelength. Nope, that's not divided by the frequency. Why am I going in circles here? Feels like one of those days. H divided by px, which I have right there. And so my frequency becomes p squared, or px squared over hm. Back on track. So that is the frequency, but I have change over there, so I need to somehow relate the two. So I need to look at the change in the frequency with respect to the momentum. Now, for some of you, this will be obvious. For others of you, it will not be. Well, we've talked about doing slopes, and what we're basically doing, if I had a frequency momentum plot, I'm looking at the slope of it. So frequency versus momentum, I basically have a parabola here, because it's p squared. What's the slope look like of a parabola? Oh, we've done this before. When we put it in a different context here, if we had a position versus time graph, and if acceleration is constant, that would be a parabola. The formula is my position is equal to my initial position plus VIT plus 1/2 AT squared. That's my formula. That's a quadratic. What's the slope of position versus time?
Speed.
Or velocity? Yeah, I'm not drawing the vector symbols because I'm doing that quantum laziness thing.
Word.
What's the speed versus time or velocity versus time graph look like?
Acceleration.
Oh, no, it's just,
With,
it's a linear
Oh.
function.
yeah, okay. So the slope of this would be a line. Matter of fact, I know that V is equal to whatever my initial speed is plus AT. Well, notice that 2 and the 1/2 basically disappear there. So the same thing's gonna happen over there is that I don't have the half, so the 2's gonna stick around. But my slope here, the change in F over the change in P, is gonna be equal to 2P over HM. So therefore, delta F is equal to 2P over HM times delta P. I'll have to flip back to that in a moment. So delta F is equal to 2P HM times delta P. I know that delta T is equal to, jumping back, M over P delta X. So if I multiply my frequency times time, or change in frequency times time, times change in time, I get 2px hm delta p times m over px delta x.